AI Scientific Software and Coding Workshop series. Before we get started today, just a couple housekeeping items. Um, as you may already know, we do have a code of conduct. So when you registered for this event, you did agree to abide by this code of conduct. Essentially, please be respectful of our speaker today and for folks in the chat. If you run into any issues, please feel free to contact one of us. Our emails are listed on the slide here. We wanted to share our very last workshop session for this workshop series. It will be on Thursday, January 23rd from 2 to 3:30 p.m. Mountain Time. It will be fully virtual on Zoom, and this will be a lightly moderated session with a discussion on generative AI tools for coding beyond GitHub Copilot and Gen AI applications beyond coding and other useful tools. Because a lot of our previous sessions were kind of sit back and listen, we wanted to have our final wrap-up session be a little bit more interactive. So we would like to invite anyone who is interested in giving a 3 to 5 minute lightning talk at our last session about tools, Gen AI tools that you have used, success stories, any challenges that go beyond code generation. So we have a QR code here on the bottom right. We also have a link to the sign up page if you are interested. We ask that you just sign up a week before, roughly a week before this session, so we can get all the logistics set up. If you have any questions on this, you can reach out to Megan with her email that is listed on the slide. All right. Outside of that, I'm very pleased to introduce our speaker for today. Pengfei Li is a final year PhD candidate in computer science at the University of California, Riverside, advised by Professor Xiaolei Ren. Prior to his PhD, Pengfei obtained an MSE degree from the Laboratory for Computational Sensing and Robotics at Johns Hopkins University. And Pengfei's research aims to develop trustworthy, equitable, and sustainable machine learning systems that improve the efficiency of real-world systems and addresses critical societal and environmental challenges. His talk will be on towards environmental responsible Gen AI, carbon, water, and beyond. As a reminder, please put any of your questions in the chat. Pengfei will answer them at the end, and you can also raise your hand at the end of his presentation if you have any questions. All right, and now I will turn it over to you, Pengfei.
Yeah, thank you so much for your introduction, and let's start. Wait a minute. Okay, can you see my slides?
Yes.
Okay, yeah, thank you so much for your introduction, and I'm Pengfei. My PhD study mainly focus on environmental responsible AI, including trustworthiness, equity, and robustness. So today I'm going to talk something about the environmental responsible generative AI, mainly talking about its environmental impact about carbon, water, and beyond. So beyond includes health impact and other impacts. So let's start. So as we see, there's the AI is booming, and we have seen AI has shown its potential in a lot of different applications, and a lot of people believe that AI will shape our future and change our lifestyle. But we have seen that the AI model is becoming larger and larger, and some researchers call it scaling law. So some recent study from OpenAI says there's scaling law observed in the generative AI models. Um, so the scaling both it's both I mean the scaling is it reflected in terms of its the size of data set, the amount of compute required to train model, and the number of parameter that is used to support generative AI services. And as you can see in the figure, the model is larger and larger. And scaling law means if you want to keep improving the performance, you have to scaling up all the three parameters that I mentioned exponentially. Yeah, and some researchers find that it's mainly because larger models enjoy better sample efficiency and that means it usually require more energy. So some audience may know that these AI models are hosted in warehouse level data centers. These data centers are usually energy intensive, and the computing of AI contributes a lot to the energy consumption. So some international agencies and companies predict that the electricity demand of AI computing will increase by a large margin in a few years. And IEA, the the International Energy Agency, also project that the global AI computing energy consumption will grow 10 times from now in 3 years. So that is a high level idea of what the AI computing energy will go. And let me give you some contextualized number to give you a intuition about that. So for training, let's see. So for some early models, it's according to their technical reports or papers, they are believed to consume around 1,000 megawatts hour. And for some most recent models like Llama 3, it's the energy consumption is about 20,000 megawatts hour. So maybe some audience may ask why the GPT-3 is I mean the model size it's the model size of GPT-3 is 175 billion, but it consumes less energy than the Llama 3 with 70 billion model. That is because, as I mentioned, there are three factors that's driving the AI models larger and larger. So one of it is the size of data set. So according to the Meta's report, the the data set used to train the Llama 3 is 7 times larger than Llama 2. And Llama 2 is also believed to, I mean, the data set of the Llama 2 is believed to be similar to GPT-3. And yeah, so we only have the GPT-3. Why we are not talking about GPT-4? Because OpenAI never tell us about the details about GPT, the training energy consumption of GPT-4. But some study estimate that it's 7,000 megawatts hour. I think it's a pretty conservative estimation, but we don't know the true value of that. So let's go back to the Llama 3. So what this energy consumption like 21,000 megawatts means? So I collect some data from Department of Energy in United States. It says the average home electricity consumption monthly is around 0.8 megawatts. And yeah, why I'm comparing the energy consumption of AI model training to monthly bills, that is because usually these models are trained within like 1, 2, or 3 months. So I think it's a reasonable comparison. And also, according to the ESG report of BMW Group, each car they produce, it will consume around 2 megawatts hour. So translate it to translate the now we can translate the energy consumption of Meta's Llama 3 model to the energy consumption of monthly monthly electricity consumption of United States home. So that means training Llama 3 model, the energy consumed to train the Llama 3 model can power up around 24,000 homes in United States, or it can be used to produce around 11,000 cars, according to the BMW's report. So that's a lot. So that's only training, and actually inference is also a large portion of the energy consumption of AI models. So but before I dive into the details of the inference, I have to say the configuration really matters. So when we are talking about inference, we need a lot of context to say what is the energy consumption of each inference. Let's say here is a table from Microsoft's recent paper. They are evaluating the energy consumption of Meta's Llama model, and as you can see. the question that you ask and the answer you get, the length of that really matters. So if you ask short questions, the energy consumption is lower. If you ask longer question and the answer is also long, the energy consumption is high. And even for the same input and output, the the hardware configuration also matters. Like for this one, it's changing the parallelism that how many GPUs that you use to host the large language model and the frequency of the GPU. So you can see even within even for the same input and output, such variation can produce like two times different energy consumptions. And yeah, so that means um, both the service type and the hardware configuration matters. And there's another factor that matters is the service level objective. So here are two examples of that. That is P50 and P99. So P50 means the mean, or you can perceive at the average latency requirement for the service. Like when you are using the ChatGPT, you don't want to wait for 1 hour for it to respond. And P99 is the tail latency. That is in the worst case, what is the time that you have to wait before you get the response. So so maybe it's too abstract. Maybe I can give you a quick example about that. So you can imagine here's a here's a bus in Denver. Um, if you observe, if you take a look at that, in most time, maybe there are only 10 or 20 people. I think it's about 10 people on the bus. So maybe you ask, what if I choose smaller bus, so it can save some energy, right? So if you change this large bus to a small bus, then you can save some energy, and in average, I mean, in most of the time, you are not affected because it's far from full. So, but that means that it doesn't affect the P50 latency, but P99 will be affected by a large margin. Like let's see, imagine you are in the hot rush hour and you wait for the bus, and the bus is full. You can never get in, and you wait for a long time to finally get home. So you may be angry. So that's why that's why we have to say there are some service level objectives, and we can never provision exactly the same amount of computing resource to serve this large language model. Just like if there are 200 people taking the bus, you cannot only provide 200 seats during the day, then that would be crazy. So, so that being said, we can still get a rough estimate. If we say like the length is medium, and we choose the medium energy consumption, like say suppose it's the normal case, and let's go to the numbers. So for the GPT-4o, it's a smaller model than GPT-4, and the Llama 3 is the most popular open source, one of the most popular open source large language models. And we choose two tasks that is very common in real world lives, like writing an email and make a small conversation with ChatGPT. So you can see like a small conversation, since its output may be longer than email. So that means its energy consumption is also higher. And when you are looking at the most recent models like GPT-4 and the larger model of Llama 3, so you can see the energy increased by over 10 times. That means larger model usually consume more energy. And this is an online calculator that is publicly available at Hugging Face, and you can search you can search Ecologic's calculator, then you can find more results about that. And let's see, what does the 190 watts means. So I can give you some examples. So like for a light bulb, if you ask the ChatGPT, like say GPT-4 to write an email for you, the energy consumed can power up a light bulb for 22 hours. And there's also it can charge the iPhones for 11 cycles, or charge your MacBook for around 3 cycles. Also, it can this amount of energy can drive a Tesla 3 to 0.76 miles. So I just searched from Naka to the airport. It's around 40 miles. So that means if you ask the Chat GPT to write 60 emails for it, the same amount of energy can be used to drive a Tesla from Naka to the airport. So that is in some sense is still a conservative estimation because uh, Tesla is kind of energy efficient. But anyway, that's a high level idea of what's the energy consumed uh, during the mm, development and the deployment of generative AI models. So what's under the hood? What does the energy means? The first one is we nowadays we a lot of us know that it emits a lot of carbon dioxide and it contributes to the climate change of our globe. And secondly, our recent research fund reveals that the AI computing also consume a lot of water and it can impose some water stress to some regions. Finally, it's also related to the air pollution of certain areas that impose public health risk to some communities. So okay, let's jump start in. So let's start with the carbon. So when we are talking about carbon, actually we are in a more broader way, we are talking about greenhouse gas emission, GHG emission. So let's say this is a data center. So what is GHG? That includes several different gases, and all of them is believed to contribute to the global climate change. And different gas can be converted to, and its greenhouse effect can be converted to the greenhouse effect of carbon dioxide. So we are talking about carbon dioxide equivalent, but we are so when we say carbon dioxide equivalent, we are not only talking about carbon dioxide. So okay, so for data center, so this is an illustrative figure of data center. So where does the GHG come from? So we divide it to three scopes. The first scope is onset. So like for the data center, it usually has some diesel generator for backups um, when there's electricity when there's electricity outage and their diesel generator can be used to back up and keep the service running. And yeah, so in addition to that, these diesel generator have to be checked routinely to make sure it's in a good shape. So it directly emits some carbon dioxide on site. So what we call it scope one. So scope two is the carbon dioxide associated with the electricity generation process. So depending on the fuel mix used to generate electricity, this indirect carbon emission also varies spatially and temporally. And thirdly, that's scope three. Scope three it's the um, in some sense it's a life cycle analysis. That means um, the fabrication of the AI chips and the construction of the AI data centers. It emits some carbon emissions, and we can calculate that and put it as a scope three carbon emission. So let's go back to the larger. Oh, before I proceed, I have to say most of the carbon dioxide of the AI data centers is from the scope two and scope three. And when we are talking about like Llama 3's carbon emission, it's mainly about scope two. So if we consider scope three and scope one, the number is higher, but we can we can we can stick to the number that Meta provided us. So for the training, according to the Meta's report, it's like for this Llama 3, for 405 billion model for this model itself, it emits around 89 8,900 tons of carbon dioxide. This amount of carbon dioxide is equivalent to producing around 300,000 Apple Watch and around 56,000 laptops. And maybe maybe some of you has seen that it also reports a market-based carbon footprint and location-based carbon footprint. So what does that means and why the market base is zero? So let's give you some example. So suppose location based, suppose you are using 100 1000 100,000 kilowatts hour electricity and your location-based carbon is multiplied by the grid emission factor, the average grid emission factor of the electricity grid locally. That depends on the fuel mix, but we can get a average of that and calculate the location-based carbon emission. So in this case, it's 100,000 times 0.21. That is the total carbon dioxide. And when we are talking about market base, so suppose the large company, they can make contract with some renewable energy companies and purchase renewable energy from them and obtain a REC, renewable electricity certification. In that sense, if they buy out all the electricity consumed for their model training, they can say, okay, my carbon emission is zero. But if they don't buy anything, the factor of multiplication is higher than the previous one because the the renewable energy is already sold to some other companies. So you have to choose I mean, when you are calculating, you are choosing the non-renewable ones or the renewable left in the market. So this number is higher mm, than the location based. But Meta, according to their ES report, they claim they have purchased 100% um, renewable energies to support their model training and inference. So as a resident, if you are interested, there's also a lot of websites that you can get a REC, Renewable Energy Certificates. These organizations will plant trees or collect greenhouse gas emission from farms to offset your electricity consumptions. And you just have to pay some money to get it offsetted. For big techs, they have more approaches and more flexible ways to purchase REC, but that's a quick example about what is market-based and what is location-based. So for location-based, not all regions are equal because let's say for California, it has more renewables like solar and wind. The carbon intensity, I mean, the carbon emission for each kilowatt hour electricity. That is carbon intensity. So its carbon intensity is lower because it has more renewable energies. And for some other states like Utah or Wyoming, it has more fossil fuel based power plants. So that's why their carbon intensity is higher. So I just showed there's spatial variation, but there's also a temporal variation. As you can imagine, the first one is Texas. So as you can imagine, in the daytime, we have more solar available to use. Then the carbon intensity is lower. But when at night we don't have a large amount of solar energy. So in this case, they are using natural gas to power the electricity grid. So in that sense, the carbon intensity will increase at night. And similarly for California, it's the same. Renewable is more abundant. Yeah, the renewable is more available than in the daytime than the nighttime. So yeah, so there are a lot of variation in terms of spatial and temporal. And let's go to the water footprint. So the first part is from the offset water. So the offset water is similar to the carbon intensity that I just talked about. So depending on the fuel that used to generate the electricity, this factor also changes during the different time of day and across different locations. And for on-site water is kind of different because uh, that that's a water evaporated uh, in the data center. So let's say for the data center, we need a we need to bring the heat from server to the outside. So there's two loops. There's an inner loop. There's an inner loop and outer loop. Inner loop is only taking the heat from inside to the heat exchanger. So there's no water consumption unless there's a leakage in the pipe, but you already know. You already the inner loop don't consume water, and for the outer loop, it's taking the heat and bring the heat away by evaporating some water, and this is what we call it onsite water. So there are several factors that affect the on-site water and off-site water. So for the on-site water, there are two main factors. The first one is white bulb temperature. Just you can imagine, in the hot days, you sweat more to cool down your body. So similarly, for data center, it also evaporate more water to cool down the server. That means its WUE is higher. And similarly, for the number of cycles. So number of cycle means the number how many times you use the water before you dump it to the drain. So the more cycle you are using, then the less water you consume. And next one is the offset water intensity. Similarly for the carbon, similar as the carbon, it's affected by the fuel mix that is used to generate electricity. So we have to reinforce that the carbon intensity and water intensity is not the same thing, just as it shows. So just you can imagine in the daytime, you have more energy, you have more renewable energy like solar, then the carbon intensity is lower. But actually, daytime is kind of hot. So that means you will require more data to cool down the server. So there are several locations, and all of them demonstrate that it's different. So that being said, we can still get an estimate of the water consumption that used to power the GPT-3 model. So here's the number from our paper that you can see there's a large variation even inside United States. And we also draw a figure for the world. So as you can see, maybe United States is in the middle, but for some European countries, because they are more relied on, some of them are more relied on fossil fuel uh, energies. Then that means it's consume more water to support the AI inference. And our research has increased the public awareness of water footprint of AI models and influenced the policies of some international agencies, including WHO and UNESCO. Okay, so next one is health risk. So So as I mentioned, the fossil fuel for some locations they are more relied on fossil fuel power plants, and the electricity generation of the fossil fuel power plants can produce plenty of air pollutions, including nitrogen dioxide, PM2.5. These air pollutions are some researchers in public health has revealed that these air pollutions is related to the increase of air pollution related mortality and mobility issues such as asthma and lung cancer. So also there's for the PM 2.5, there's recently there's a lot of research reviewing their long-term and short-term health impacts of exposing to such air pollutions. But this air pollution is not only taken by the local, because the air pollution can travel thousands of miles. And I think there's a lot of expert in this in our audience, because it's an atmosphere research center. So we know there's a dispersion process. So so the air pollution can travel a long distance within several days. So and such air pollution can have yeah can affect the especially the children's health and impose a great public health threats. So let's recap. So AI computing has great has a lot of environmental footprints and it's affect our society in different aspects. So so after knowing such impacts, so what we want to know is what we can do. So what we can do to reduce the carbon emission, the water consumption, and the air pollution to make the world a better place. So some big companies already take some procedures, like say this is an example from Google. So Google is trying to relocate its Google has a lot of data centers across the world. So as you can see in this illustration, uh, Google is trying to relocate its computing from carbon intensive locations to some locations with more green um, uh, with more renewable energies. And in that sense, it can reduce the carbon emission of the of the computing without impacting the users' experience, users' quality of experience. And not only Google, there's Meta and Microsoft is also trying to make the inference more flexible, both spatially and temporally. And there's also some national agencies like Department of Energy that has some white papers to urge the data center to respond to the environmental impacts and adjust their computing according to some signals like carbon intensity. Now, let's say it also can respond to health impacts. But there's a fundamental challenge um, in this goal. That is, let's go back to the large language model and as I mentioned, we can route the user demands to several different locations and serve the user demand using the computation hardwares in these data centers. But as you know, the user demand may fluctuate a lot during different time of day. So we have to reconfigure um the hardwares to support such inference. And since we don't know what will happen in the future, so this is an online decision process, and it's really hard to make a global optimal solution. Let's give you a talk example. Suppose here left is the demand, right is the server. So as the demands fluctuate due to your scheduling or the demand itself, you may have to turn on and off some servers or reconfigure some computing hardwares from other tasks to this task. So you can see it's actually during this fluctuation, you are turning on and off some servers really frequently. It's not very good for the server, and it can also cause some incur some costs associated with your switching actions. So that's a quick example that illustrate that this online decision is hard because you don't know what will happen in the future, but you have to make decision at the current stage. So, so my research, my PhD research is mainly focused on this area, and the three main components of it is the first one is trustworthy machine learning augmented algorithms that is use machine learning to make more intelligent decisions to help us reduce the environmental impact of AI models. And secondly is sustainable AI that is involved with modeling the environmental impact of AI computing and identify the areas that we can improve to reduce the environmental impact. And finally, it's an equitable AI system. It's trying to uh, reduce the uh, reduce the environmental impact of AI computing in a more equitable way. So let's go to the first one. We call it smooth online convex optimization. Just as that example, we don't want to switch on and off the server too frequently. So this is the mathematical formulation of this problem. So F is we call it heating cost. That is how well you are serving the user demand at the current stage. And the second part is switching cost. That models how frequently you are switching on and off the server or reconfigured hardwares or similar stuffs. So it's for here, for ease of presentation, we only consider the switching cost is only the difference between current stage and previous stage. But actually, you can consider longer memory to incouple to incorporate higher order dynamics of the system. So this is the online decision making process. You you only receive at time step one, you only receive Y1. So Y1 is the context. So you receive context, you make decision, context, decision until the end. So we care about the two metrics. The first one is average, and second one is the compare ratio. So the average is the average case, and compare ratio measures the worst case. So we want the we want some algorithm to perform well both in terms of average case and worst case. Uh, worst case. And yeah, so here's a quick example about responsible AI computing. Here's I think it's November 12th. So here is the nominal day of the film mix in California. But actually, you can see different from this day. Other days may have different uh, uh, film mix depending on the that day's situation, and you have to make decision based um, on the film mix and the user demand of that day, but you don't know what really happens at that day. Let's say in the future, we don't know, and you need a policy to do that. And that policy, as I just show you, the greedy policy that you greedily follow the the carbon emission rate of that region, that will do a good job in terms of the current stage, but actually frequently turning it on and off will incur a very large switching cost and negatively impact the quality of experience for the users. So this problem actually we can see this problem as a online decision process that the policy based on the currently available information to make decision, and then the environment give the review the cost of that decision. So there's some algorithm that has been designed to deal with this problem by investigating the property of the function and guarantee the worst case of the algorithm. But actually, in terms of average performance, there's still a lot of room to improve. Let's say we have for the AI computing or the scheduling, we have a lot of historical workload trace or historical information. What about using this information to help you make decision? In that case, there's a lot of algorithms recently that use machine learning model to learn some patterns from the data the data samples and make the decision more intelligent. So in the high level, this algorithm can divide it into two categories. The first category is, okay, let's say for the renewable energy. So we can use historical data to predict what is a few mix in next few hours. Let's say how much solar we can get from the electricity grid. So yeah, so based on that information, also the user demand, we can also predict that. Based on that information, we can use that information to optimize the um, the overall cost and improve the performance. But there's also another category that is using the machine learning model to directly tell us what we should do. And This is more direct, but all of them face a fundamental challenge is the machine learning model is not reliable, especially for the online decision process. It may create some future impact that is not available or not unforeseen at the current stage. So that means its worst case performance may be bad. So so these are the two types of algorithms, and my goal is to combine them together to get both of best of both worlds. So let's say for this figure, so we have in terms of robustness, expert is better, but in terms of average performance, it's worse. And for the machine learning model, it's opposite. So our algorithm is trying to combine them together and trading off the performance and robustness. And most importantly, we want it to be adjustable because different users may have different preference. Some users care more about the performance and it doesn't really care about robustness, and some users are the opposite. So from mathematical formulation, that is, we provide a parameter lambda. So by tuning the lambda, we provide different robustness guarantee to the algorithm, and so the consistency is how well you are performing compared with machine learning. So we can take this parameter to trading off between the performance and the robustness. But this goal is highly non-trivial. Let's say there's maybe we can have a straightforward idea is okay, let's say for each step, we can make sure suppose we can make sure uh, the the cost of our algorithm is always smaller than the cost of the expert. So is that possible? Actually, um, it's impossible because even if in the current stage your cost is equal to the lam to a scaled version of expert cost. In the next stage, it's also possible to incur a very large cost because when we are talking about switching costs, it highly depends on the previous action that you are choosing. So even if at this time you choose the exactly same action as the expert, because let's say if you are turning on so many servers at certain stage, then if even if you choose the exactly same action as the expert, you are still incurring a large switching cost. So take home message here is um, if you simply say um, at current stage you are smaller than the expert cost, you in the future you are still you it's also possible to face some difficulties that you can never recover the cost. So as I mentioned, there's a here is as the figure shows. So even if we choose the same action as the expert, our algorithm's cost is still larger than the expert. That means the constraints. You can never find a feasible action in the constraint. Um, but if we introduce an additional uh, reservation cost like this one, so though the green line may be longer than the blue line, but if we say we add a reservation in the previous step, so the red and the blue one together is smaller than the green one. So that means our algorithm can always choose expert algorithms as a backup option if we consider such reservation cost. So intuitively, if we have an expert that give us a decision, we can use that decision as a constraint, and the lambda controls the diameter of the constraint. So if we have larger lambda, that means we put a less strict requirement on the robustness. In that sense, we have more flexibility to follow the machine learning advice. So machine learning advice is the red dot we are projecting the machine learning device to the constraints. So if the circle is larger, then it's possible eventually you can completely follow the machine learning device. So here's the algorithm. Here's the algorithm chart of our approach. So each time you receive some advice from machine learning model, and you feed this machine learning model to the robustification process to give you the calibrated action. And finally, you get a cost from that and repeat this price process until the last round. And here's some theoretical analysis, but I can go over really quick. So the combined ratio here is robustness and consistency. So by tuning the lambda, if you put the lambda larger, then the consistency should be smaller. That means you are performing better in terms of following the machine learning. But if your lambda is uh, is large, then you are facing worse robustness. So let's go back to the application. So the heating cost now, let's say the heating cost. The heating cost is is how well you perform at the current stage. So the context of the heating cost here is the user demand, the energy fuel mix, the water intensity, and air pollution of the current electricity grid, and the 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 data center's operational information. Based on that information, you can make decision, and such switching cost is the hardware reconfiguration cost, and also the thermal configuration that you have to adjust to, like if you have more computing at the current stage, maybe you have to turn the AC lower. That's the example that you have to frequently, if you are changing your configuration, you have to change some configuration to satisfy this demand. Yeah, so given the heating and switching, you are optimizing the overall cost of the AI computing system, and using our algorithm, you can get a better job. You can do a better job. But there's still a limitation in this one. That is, we are not really considering the equity in the AI computing system. Let's say, for example, as I mentioned, California, in terms of energy fuel mix, is greener than the Utah. So if we only care about the overall carbon emission or overall environmental cost, we should schedule all the user demand to California. So let's say for air pollution, California, let's say three, this is a top example, three. Suppose we have three users, and if we schedule all of them to California, then the air pollution in California is higher. It's all of them is from all of the air pollution is incurred in California. But it's actually it's not fair. We should consider another approach is make it more equalized. And in terms of air pollution, it's also equalized. And this is very important because some recently some media coverage shows as the big techs are building more data centers and routing more AI computing demands to some locations. It impose some local environmental impact, especially for the low-income communities. So in that sense, we have to do something to not only reduce the overall the overall environmental impact, but reduce it in a more equitable way so that the all the society can be benefited from the AI generative AI models at large. Yeah, so that's our future work. So due to the time constraints, I will not go into the details of that. But now I'm happy to take any questions. And thank you so much for your attention. Yeah.
I put it in the chat so everybody can read along. I really appreciate the details. I had a question specifically on kind of the reporting. It looks like you had to do a lot of digging through shareholder reports and, finding information that's not exactly easy to find. I appreciate that. Are you aware of any emerging reporting requirements or regulations, even in the proposal phase? I'm thinking earlier this year there was the Department of Energy almost rolled out regulations on crypto, right? And then they were deferred for some industry pushback, understandably. I was wondering maybe where the AI world sits in that same space, if you have any awareness.
Oh yeah, so I think they are yeah I think there as AI computing is more and more popular and I have seen some recommendation or regulation regulations policies to ask the AI the big tech companies to report their uh, carbon emission and air pollutions. But I think one thing is reporting, but another thing is how to reduce such impact. So so that depends on the scope of your first I think first that depends on the scope of the emission. So as I mentioned, there are three scopes. So the first two scopes, it's kind of uh, it's relatively easier to obtain because how many electricity consumed that can be retrieved from the electricity utility companies and based on the electricity grid carbon intensity we can get so the public can get an estimate of that and similarly for the diesel generator or backup generator it's also well documented but for the scope 3 it's kind of tricky because that relies on the whole supply chain and some some companies may focus on the the supply chain that is directly related to their AI computing, but some companies may focus more on the long chain. So it's kind of tricky depending on what scope you are talking about. So I think now DOEs are trying to make the AI companies to get a more comprehensive analysis of their environmental impacts. And they are also trying to, one thing is, one thing is reporting, and another thing is trying to ask them to respond to the environmental impact. For instance, um, in some nighttime or some other time we don't have enough we don't have a lot of renewable energy so if the AI data center is flexible to reduce their computing or reduce their energy consumption it would be great for the whole society to reduce the to reduce the carbon emission and health impacts so it's also important for them to respond to the need so in general we have so when we are talking about capacity or gen electricity consumption, in general, we have a lot of energy available to use, but when and where to use the energy is the key thing. Yeah. So so
Yeah,
that matters.
thanks. I'm glad to hear there could be some reporting because, until it's really equally measured, it's hard to manage. So appreciate it. Thank you.
Yeah, yeah.
And it looks like we have time for one more question, and that's coming from the chat. Do you have any sense of the training and inference energy costs with Google's Gemini, similar to GPT and Llama? I wonder how expensive my Google searches are now that Gemini is always responding to search engine queries.
Yeah, very very good question. So actually for so all the information that I obtained is based on the self-reporting of the big techs. So from to the best of my knowledge, I was trying to see the Gemini's energy consumption both in inference and the training, but I didn't find enough data for that. But I think it would be comparable to the public available models, just like Llama. So GPT is also some in some sense is kind of outdated because it's only GPT-3. Starting from GPT-4, they won't say anything about the energy consumption of that. So yeah, so for Google search now it's trying to integrate the Gemini to the search, but just as I mentioned, the configuration really matters. So depending on what model they are using, and uh, yeah, some people, I mean, some users can have the Gemini integrated to their search, but some of them are not, because for me, maybe I didn't turn it on, so I didn't see the Gemini, but in my wife's laptop, I see that several times. So my personal suspicion is maybe they are also trying to scheduling the demand. So if there are fewer people using that Gemini, maybe they can. I mean, if there are fewer people using the Google search, they can get a larger portion to a larger portion of the search to the large language model assisted functions. But if there are more people using, maybe they can reduce. So in that sense, the flexibility allow them to make the AI I mean the inference of larger model more efficient. So in that sense, maybe their number is lower than what I provided. So that really depends on the yeah. Yeah, they are packing the past. Yes. So I think that really depends on how they operate and how they schedule their demands. Yeah.
Great. Thank you so much for your time, Peng Fei. That was really interesting. And so that's it. That's all that we have for our fifth session for the Gen AI series. In the chat, I am going to put the save the date for our final session. This is our wrap-up session for the workshop series. If you are interested in doing a 3 to 5 minute lightning talk, I have the information in the chat to sign up, and we'll also send out an email as well if you are registered for this workshop series. Thank you so much. Hope you all have a